we've discussed some of the simple gas laws. There are a couple of other ones. But we can combine those simple relationships that we've looked at so far and come up with an equation that relates all four of them. And the book goes over how that happens. I find that most students are not that interested in it, and so we're just going to cut to the chase here. PV equals nRT. Sometimes people call this PivNert. This is the ideal gas law. So we've got the pressure times the volume is equal to the moles of gas times R times the temperature. R is called the ideal gas constant. And when we're using liters and atmospheres, it's going to have this value, 0.08206, and the units look strange, but the units are there to cancel out all the other units. So liter atmospheres per mole Kelvin. One thing I'd like to show you is that you can take the ideal gas law and make any simple gas law that you need. So we can take one ideal gas law and divide it by, so P1, V1, N1, T1. R is always the same, so it's not going to have a number. And divide by another ideal gas law. The ideal gas constant is always the same, and so that will cancel out. So let's say that the pressure, we're going to do, let's do this one. Constant N and constant pressure. If the amount of gas is constant, that means that the initial moles of gas is equal to the final moles of gas. They are the same, right? And so then if N1 is equal to N2, those cancel out. And this also says the pressure is constant. Whatever the initial pressure is equal to the final pressure, and so those cancel out. And so then we've got V1 over V2 is equal to T1 over T2, which looks a little bit different than Charles' law, but if we rearrange that, we get exactly the same thing. So you can take one ideal gas law, divide it by the other ideal gas law, cancel out anything that's not changing. And that will leave you with the equation that you need. There is at least one problem on the worksheet where you need an equation that's not actually given in your textbook. And this is the best way to come up with that equation. So let's do an ideal gas law problem. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? So we've got 8.5 liters, we have 0.552 moles, we have 305 Kelvin, and we want pressure in atmospheres and PSI. So I'm going to write these numbers down. 8.5 liters, 0.552 moles, 305 Kelvin. And then let's identify these. 8.5 liters, is that volume, pressure, temperature, or moles? That's the volume, right? So that's the volume. And what about 0.552 moles? PV, N, or T? That's going to be N. And how about 305 Kelvin? That's going to be T. So our ideal gas law, PV equals nRT. Here, the question is, what's the pressure? So we're going to rearrange this to find the pressure, divide by volume. So pressure is going to equal N times R times T divided by V. Well, they didn't give us R. Bless you. R is 0.08206 liters atmospheres over moles Kelvin. These are the units that we have to use in the ideal gas law. So we can plug everything in here. I've got 0.552 moles. R is 0.08206 liter atmospheres per mole Kelvin. Just going to do a little magic there. Temperature 305 Kelvin divided by the volume, 8.50 liters. Write all the units in. So my moles are going to cancel here. My kelvins are going to cancel, and my liters are going to cancel, which leaves me with atmospheres. So 0.552 times 0.08206 times 305 divided by 8.5. Pressure is equal to 1.6254 atmospheres. And looks like everything pretty much had 3 sig figs. Any questions so far? I think in some ways the ideal gas law problems are easier. Yes? Where did the R come from? The R is the ideal gas constant. And that's a number that they had to put into this equation to make, it's kind of hard to explain. So the pressure times the volume is proportional to moles times temperature. So the ideal gas constant is basically a proportionality constant. Yeah. And so a lot of people end up memorizing that, but it'll also be given to you. So you can always look that up. But it will almost never be given in the problem. So you write out ideal gas law, PV equals nRT, and you're like, I have everything but R? Yeah, let's go look it up. Good question. So they also want the answer in PSI, and so then we would need to convert from atmospheres to PSI. And again, pressure unit conversions are always just a single step. So we would go to our pressure unit table, and we would see that 14.7 PSI is equal to 1 atmosphere. And so this would be 23.893 PSI. And so my answer would be 1.63 atmospheres or 23.9 PSI. Here's another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So, got that many moles, and I got that pressure, and I got this temperature. and they want the volume. So 0.556 moles of gas. They don't tell me what that is, right? But moles, that's the amount of gas in moles, that's what we call N. And then they do come out and say that this is the pressure, 715 millimeters of mercury. And the temperature is 58 degrees Celsius. And then the other thing we're going to need is that ideal gas constant. The units on the ideal gas constant tell me what units I have to use for the other things. Do I have all the correct units? No, I don't. I have pressure in millimeters of mercury, so I'm going to have to convert that to atmospheres. So multiply by atmospheres, divide by millimeters of mercury. We go look that up, and 1 atmosphere is exactly equal to 760 millimeters of mercury. So I've got 715 divided by 760, 0.94. 0.79 atmospheres. Again, you want to write down a couple extra digits. The temperature was given in Celsius, so we have to convert that to kelvins. .331 kelvins. I've never seen a pressure gauge with units of atmospheres on it. I've also never seen a thermometer with units of Kelvin. So the pressure and temperature you're often going to have to convert. So now we've got all the units that we need. PV equals nRT. I can rearrange that by dividing by volume. I'm sorry. I could do that, but that wouldn't help me. I want to get rid of the pressure. So the volume will be equal to the moles of gas, 0.556 moles, times the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, times the temperature in Kelvin, divided by the pressure in atmospheres. .556 times 0.08206 times 331 divided by 0.94079. 16.052. And if we check our units, the moles cancel, the atmospheres cancel, the kelvins cancel. And the unit here is liters. So my best answer would be 16.1 liters is the volume. Any questions? Okay, one more problem here. Determine the pressure in millimeters of mercury of a 0.133 gram sample of helium gas in a 648 milliliter container at 32 degrees Celsius. None of the units are right. None of the units are right. So we're going to do a lot of unit conversions here. So we've got a mass of gas, and we have a volume in milliliters, temperature in Celsius, And then they want us to find the pressure in millimeters of mercury. Nice. Okay, so the first number I come to is 0.133 grams of helium. And then I've got 648 milliliters and 32 degrees Celsius. Well, 648 milliliters is the volume, and 32 degrees Celsius is the temperature. And this is related to the amount of gas in moles. Can we convert grams to moles? Yes, we can. So we just need to use the molar mass of helium. 0.133 divided by 4.003. In the ideal gas law, it's always liters, not milliliters. So we're going to have to fix that one also. 3.2. I'll keep my 3 sig figs and 2 more. So that many moles. Yeah, and so this is milliliters. So we could do that little trick and say, well, it's 648 times 10 to the minus 3 liters. And then here we need to add 273. And N is how much gas there is measured in moles. So we had to convert the amount of gas from grams to moles. We had to convert the volume from milliliters to liters, convert the temperature from degrees Celsius to kelvins. And R is always the same. It's asking us for the pressure. So take the ideal gas law and I rearrange it and I come up with P equals nRT over V. So then we can plug these numbers in. I'm going to have space issues. Let's do this. I'm going to write it down here. So the pressure is going to equal the amount in moles times the ideal gas constant times the temperature divided by the volume. One 1.2833 atmospheres is my pressure. But they want it in millimeters of mercury. 1.2833 atmospheres. So I can convert that to millimeters of mercury. It's 975.29. 975. I'm going to go up. 975 millimeters of mercury. Any questions?